Hi, everyone. Thanks for joining and welcome to the Embedded Working Group meeting. My name is Maria. I work in Proxima with Pablo Garrido, the technical manager of micro-ROS, and together we are hosting this Embedded Working Group monthly meetings. Please, we kindly ask you to add your names to the attendee list in the document I'm sharing with you in the chat. Thank you very much. So, as you must have seen in the agenda for today, we will start this meeting by introducing new RCLC features and hardware in the loop update. Pablo Garrido will be updating us on RCLC QoS API, prepare executor, callbacks context, timeout, and also he will be making an update on the hardware in the loop for micro-ROS. And this update session will be followed by one live presentation and one panel discussion. The live presentation will be covered by our special guests from Sony, Tomoya, Fujita, and Koizumi Takayoshi, and they will be telling us about a Sony project related to integrating micro-ROS and the Sony SPRESENSE 10 board. So they will introduce the architecture and overview of this use case and the Sony SPRESENSE 10 in more technical detail. Please keep in mind that there will be some time at the end of this presentation for questions and answers. And to finish this session, there will be a panel discussion about providing a CPP API for micro-ROS. And this session will be managed by Jan Staschulat from Bosch. Hi, Jan. Thanks for bringing this topic here today. And he will explain the objective and the purpose of this panel discussion. So please, I would encourage you all to actively participate in this panel. So finally, if any of the attendees wish to treat any further topic, simply add them into the miscellaneous section of this document and will be discussed at the end of the meeting if we have time left. I want to thank the participants from Sony and Bosch for bringing us this today related to embedded applications. And let's start with the agenda. Let's start with the new RCLC features and hardware in the loop update.
Okay, I'm going to share my screen. Can you hear me well?
Very well.
Yeah, okay. This is going to be quick because I want to show you small changes that we have been doing in the RCLC API in Bosch and here in the Proxima. One minor thing that we have added to RMW and the status of the hardware in the loop that we have been talking in the previous embedded working group. The first of all is that we have added an API in the RCLC that now allows users to set custom QoSs. Until now, you only are able to use default or BSF for entities, but now we have prepared this API that allows you to use a whole RMW QoS profile. So you can set all the internal QoSs available in RMW, and the entities can be tuned to be adjusted to the use cases. We have the same API for client, servers, publishers, subscribers for all the entities. That's the first thing. Then regarding the one topic that we have been talking about, that is that the first call to executor, to RCLC executor spin allocates memory because it initialize the weight set in the RMW. We have prepared this new function that this executor prepare that can be optionally called before spinning the executor in order to make the dynamic allocations in a safe way. That way, if you call this before spinning the executor, you ensure that your application is not going to use dynamic memory in spin time. And all the dynamic allocation will be in the previous stages of configuration before spinning. I think that I have been not involved in that, but I think that Jan will talk about this later. But they have been working in adding context to all the callbacks available in RCLC. So user can provide context and provide one argument to the callback, and then the callback have some kind of knowledge of from where it's called. I think that Jan can say us something about that later. Regarding the timeout API, we have prepared an API for configuring how much time is going to take to the publisher to publish when you are using a reliable mode in XRCDDS. The point is that when you publish a topic in reliable mode in XRCDDS, in the RMW of XRCDDS, it will spin the session. It will run the session, the XRCDDS session, in order to confirm that your messages are arriving to the micro-ROS agent. And this run session method have a callback. But now, up to now, we only have a build time configurable parameter. But now with this, you are able to set it at runtime. So you can set this before publishing, and the time that the method call will block the execution will be at most this session timeout. And we think that this is interesting to have this configuration in the reliable publication. And finally, I would like to show you a little bit the test bench, the hardware in the loop test bench that we have been preparing. This is still in a private state, but I think that this week or next week we will open this, and so you can check that and check how we have been designing that. But in general, what we have here is a common G-test test suite that uses RCLC to create tests that will run against a micro-ROS code running on actual hardware. Each of these tests, for example, this entity creation, have another test here in client that has embedded code that will, here we can see the entity creation. That is the other part that is running in the micro-ROS client. The G-test suite is in charge of cross-compiling this code and flashing it into the Renesas board, and then checking the functionality of the RCLC against the RCLC. I think that we have prepared a schema that is possible to port to another platform. So here in the Proxima, we are thinking about adding some other boards like the ESP32. But if some of you have a special interest in importing some other boards to this build farm, we are super open to that, and we can talk. We will publish when we make this public, so you can check and contribute and everything. So that's all from my part, Maria. I think that now.
Thank you, Pablo. Is there any question from the audience?
To Maria Vinces. No, we have someone waiting. Maybe just refresh the web page, because I also have the button for allowing people to enter.
Okay, thank you. No questions? Let's move forward then. And now we would like you to bring your attention to Sony use case with micro-ROS. Tomoya and Koizumi have prepared a PowerPoint, a 20 minutes presentation to introduce the use case. Are you online, Tomoya?
Yes, can you hear me?
We can hear you.
Hello. Yeah.
Good. Thank you. Thank you very much.
Okay, so do you see what I see?
Yes.
Yeah.
Okay. So Sony is going to make a presentation about the SPRESENSE with micro-ROS, and I am from R&D Center based in US, and Koizumi-san is going to explain about details of the SPRESENSE. So I'm going to go quick about the overview with R&D perspective. So the first one is the introduction. Why we care and we try to use the micro-ROS is it's a good affinity and transparent with ROS2. So the robot is going to be supported by ROS2 and some microcontrollers shooting some sensing data to the ROS2 robot. So it's really good affinity and transparent we can use. And also the good community support and activity. And the last one is, I think, important. Eventually, many sensing data come from the microcontrollers. I mean, like R&D phase, and if it's not the production phase, maybe we can do whatever we want. Maybe we can set up some Ubuntu, and we can connect a bunch of sensors to that PC and see if what's going to happen. But once it comes to the product, we have to take care about real time and always that like the timestamp. So I think eventually we're going to have to use the microcontrollers to get the sensing data from the edge. And overall, it's a really easy picture, but our R&D perspective is something like this. So the cloud infrastructure is always there. It's kind of like a brain to access. So there would be the bunch of robots working together, maybe the factory and logistics, and but some intelligence, the process, or like a deep consideration will be done in the cloud. It's a core brain to access the cloud service. But near edge is actual robots. So, but it process some like consideration. It's like a collision detection or easy path planning and something like that. But it's not exactly the core brain. It's like a small brain to think about, to make a quick reaction or something. And the last one is a far edge. This is, I think, for the microcontrollers, micro-ROS. So it's not exactly moves around, or maybe it's kind of like sensor device which is connected some interfaces to robots. So there would be a lot, but it does not do any process for like a brain. It just get the sensing data and provide that sensing data to the near edge. That's our architecture. So we didn't try to use micro-ROS based on the SPRESENSE, but we did try this configuration. So the single LAN is there, and there is a couple of robots based on ROS2. It's just experimental, the PC and workstation and Raspberry Pi, and some ROS2 application is there, and the ROS2 agent is there to support micro-ROS. And we have two SPRESENSE connected GPS and gyro accelerator or something like that to get the sensing data from that hardware to shoot that sensing data to the ROS2 agent, so that ROS2 application can see that sensing data from the microcontroller. And everything works okay for now. That's what we did. And the procedure is really easy. There is no other specific procedure required to run the micro-ROS application on SPRESENSE, because SPRESENSE supports NATX. So either you can check out the SPRESENSE SDK documents to see if you can just move, you can just copy that application directory to that SPRESENSE SDK and build, and you can have a go. Or the micro-ROS NATX app procedure, you can use SPRESENSE supports NATX. So let's say just NATX procedure can be done. So that's it. So I just explained about the overview, what we think about in the future, maybe next 2-3 years, what we are trying to do, what we want to see, what's going to happen in the future. But the SPRESENSE detail will be taken care of by Koizumi-san. So the Koizumi-san is going to take over from here. Koizumi-san. Can you?
Yes, thank you. Yeah, I will share the screen. So,
yeah, there you go. We can see that.
Okay.
Yeah.
So, hi everyone. My name is Takayoshi Koizumi, and I'm in charge of SPRESENSE software development. And thank you for inviting me today here. And I'm very happy to hear that you are considering SPRESENSE are one of your official board. So please let me explain to briefly introduce of the SPRESENSE itself. And this one is the SPRESENSE is a microcontroller development board launched by Sony Semiconductor Solutions in July 2018. As a feature, it has 6 Cortex M4F cores and use very low power microcontroller, and it works in 7.7 volt, and it's also, of course, depend on the frequency, but every voltage is lower power, and also it contains Sony's audio technology and can handle 192 kilohertz 24-bit high-resolution audio, and in addition, it is possible to simultaneously in input 4 analog microphone and or 8 digital microphone. And for output, it has a Class D full digital amplifier, so which can also output high quality sound. And another feature is GPS, GNSS positioning capability, and that supported the supported satellite is GPS, GLONASS, QVSS, and Beidou and Galileo. And also the camera interface is supported. And the SPRESENSE board family is including the main board and the camera board and the extension board and LTE extension board. So this is a very new one, and actually this extension board is currently only available in Japan, and but we plan to release the EU and the US model by the end of this year. So this is the spec of the main board, and as I told you, the CPU is the Cortex M4F 6 cores, and frequency is supported 156 megahertz or 33 or 8 megahertz. And SRAM has 1.5 megabytes. And the flash memory is on board is maximum size, so the 8 megabytes. And some digital inputs as digital microcontroller. And analog input also has two and GPS, is I explained before. And camera input. The camera is here. This one is the camera input, and it's a dedicated parallel interface. And both how to say operating conditions like this. And here's the spec for the camera board. The image sensor is used Sony's one ISX012 image sensor, which was resolution is 5 megapixel maximum. And this one is kind of the iSOC. So this image sensor can generate the JPEG directly, not only the raw data. And this is the extension board. It's used to expand the I/O of the main board. So main board is attached on here and connected via the board-to-board connector, 100 pins. And this board it has the SD card slot and the headphone jack and microphone input pin here. So that's you can easily enjoy the audio function of the SPRESENSE. And this is a LTE extension board. It uses an IC called LTE 1250, manufactured by Altair. Now the company name is Sony Semiconductor Israel. And as I mentioned earlier, this board of the EU and the US model is will be available by the end of this year. And in addition to SPRESENSE peripheral boards, there are many other boards available from third parties. And unfortunately, most of the boards are still only available in Japan. And but Sony is working with them to get them deployed overseas. And the SPRESENSE chipset, it is used chipset by Sony. There are two chips. One is 65602, and the other is 5247. And 5602 is basically the digital part. And 5647 is the analog part. And this is the internal of the 5602. There are four domain block, and one is application domain. So this one is including the 6 cores and 1.5 megabyte SRAM. And usually the user can use these 6 cores to programming themselves. And yellow block is system on the I/O processing block. And actually, there is one more core. It's a Cortex M0 Plus. And this core is handling the booting up or the system management and power domain control. Actually, this one is working as a secure core. So this chip can be this chip is supporting the secure boot by using this core. And GNSS block is here, blue box. And this one also has one independent Cortex M4 core to calculate the position from the with the GNSS receiver. And one more unique block is sensor domain. This one is the kind of the sensor hub, but a bit intelligent. So let me explain this green box more detail. So this one is a kind of the sensor hub, but there are with 3 functions. The one is automatic polling of the sensor data by sensor engine here, and 2-stage IR filter exists, and event detector, which detect a peak or etc. of the sensor signal. And this block is supporting for interfaces for sensors. SKC, 2 SKCs and 1 SPI, and high performance ADC and low performance ADC, and output of the PWM 4 channels. And data path, imaginary data path of the this sensor control unit is like this. So there are sensors and input by using these paths. And by polling by the sequencer, that is the sensor engine. And after that, there is the IR filter, and the filter data will be stored into the 40 kilobyte file. And also that is going to the event detector logic to generate the interrupt. And this one is a bit detail of the IR filter and event detector. So there are 2 passes. One is to the FIFO, and one is the event detector from the sensor data. And there are 3 points to set can be set the IR filter. Sorry, there are 2 points can be set the IR filter in three places. And of course, you don't if you don't want to use IR filter, the data can be stored directly into the FIFO or going to the event detector. And what is the event detector is to detect some specific signal of the sensors. And there is some settings, upper threshold, lower threshold, or the period of the increasing or period of the decreasing. And what the purpose of this is usually the for example, if you make kind of the band device and with gesture detection, and basically, usually these sensor signal, sensor data is going to the CPU to recognize the gestures every time. But to calculate the CPU, it's much more need much more power. So this event detector is detect kind of the peak of the sensor signal. So if the band device is stable, like the guy's hand is on a table keeply, then there are no signal. Actually, there are no peak or something. So then this event detector doesn't generate the interrupt to the CPU. So CPU can sleep until detect a peak by detected by this event detector. And also, you can combine the IR filter for event detector. So event detector is not only the direct sensor signal, but also the filtered signal also can be used. So much more specific frequency characteristic can be detected. Yeah, this sensor control unit is how to say the one of the idea to decrease the power for sensing every time. And SPRESENSE development things. So this is just an overview of the stack, software stack of SPRESENSE. Pink side is hardware, and green, blue, yellow is the software. And SPRESENSE software is based on the NATEX, as Fujita-san explained. And on the NATEX, we provide several libraries by running on NATEX. So as you know, the NATEX can very flexible by using the kconfig mechanism. So memory is just 1.5 megabytes that user can configure. Not only the kernels OS things, but also these other components. And but you know, the NATEX and NATEX based software is a bit how to say a higher threshold for beginners. So we also provide Arduino library, Arduino-like library for using the SPRESENSE. So we provide the addition, how to say, add-on packages on for the Arduino IDE, and also for the SPRESENSE SDK, we provide plugin for that. And several, three third parties is providing the other development platform. The micro-ROS providing the Java development environment, and this one is also already ported in the SPRESENSE. And for the Python, the Circuit Python Adafruit is supporting the Circuit Python for this present. And the LINS, this company is providing the Python compiler, and this one is also supporting the SPRESENSE. And Necto is providing the JavaScript environment. So several third parties are also providing some development environment. And now we are focused on deep learning environment. So now SPRESENSE is supporting the 3 runtimes for executing the trained model. And one is Sony's neural network console. I think it's not so familiar to the overseas. It's a deep learning environment tool with graphical network design UI. So user don't need to know any programming skill. It's just designing by the connecting the blocks of the running. And now SPRESENSE SDK can support the Google TensorFlow like micro-ROS controller. I think I don't need explain anything for this. It's the most famous deep learning development tool, I think. And Agimpulse, this is a company to provide kind of the integrated development environment for Edge AI. So the background, this one is use TensorFlow, but this tool is connected to the edge device like SPRESENSE directly, and how to say the collecting the data to run can be collected from the board itself, and the data can see the like this, and also you can design the network of the deep learning and run. And after that, run the model can be deployed directly from this tool to the device. Yeah. Now,
sorry for interruption. Yeah. How many more slides do we have?
One more.
Sorry. It's been taking a long time. Yeah.
Okay. Sorry. Yeah. And yeah. This is SPRESENSE, and if you yeah, as Fujita-san said, there are a document here. So if you are interested, please take a look. Thank you. Sorry for long.
Thank you. Thank you. Thank you very much for this great presentation. We are happy that Sony is taking initiative to adopt micro-ROS in the SPRESENSE 10 board. For sure, this will bring new industrial applications in the near future. Is there any question?
So I have two questions. Thank you very much for this interesting talk. In the first presentation, there was an arrow drawing for communication between two SPRESENSE boards that goes via the micro-ROS agent probably, or do you have some additional communication channels directly between the boards?
No, we are using the wireless network, so not the hardware interfaces.
Sure, yes, but the communication in micro-ROS will go through the agent, right? Or did you add here?
Yeah.
Okay.
Yeah.
Exactly. I have a question on the event detection mechanism. So I understood that you can somehow program it also with levels, and is there also possible to directly include the bouncing, because that's a typical problem which I saw in the past, that then working with switches or other sensors that bounce, that you get a lot of interrupts just to decide, okay, these ones are just bounces. Is that doable directly in this filter?
Oh, sorry. Your question is here, okay?
The event detection, yeah, and the event, or I think the next slide, it was even slide 12.
Oh, next one.
Yeah, I understood that I can program here the thresholds for rising and falling, and is it also possible to give to avoid the bounces if let's say a contact gives 100 events in 1 microsecond or in 1 millisecond, to avoid that these ones are counted separately? Is that possible?
Yes, you can program this one, and this one is kind of just a counter on or level checker. So usually this one is a maximum polling rate. Of course, depend on the maximum polling rate, but about until 1 megahertz sampling. It support, yes.
Okay.
Maximum.
Okay. Yeah. Thank you.
Okay. I have a last question, really quick. This presence board seems to be very complete microcontroller with extensions from even cellular IoT, CATM1 and NB-IoT, LTE and 5G, probably NSA, 5G NSA. You also know the time to market, which is the end of the year. So I'm wondering, which are the key sectors, key applications that this microcontroller is targeting?
Oh, currently some customers we are talking is mostly they are focused on audio input, especially the high resolution audio, 192 kilohertz. So this sample rate can be detect how to say super sound. Yeah, and that is good for the predictive maintenance of the factory, in a factory. So yeah, someone the customers we are talking, half of the customers we are talking is interested for the predictive maintenance by using this high resolution audio input.
Really interesting. Thank you.
Yeah.
Thank you very much.
Also just one quick question which goes in a similar direction. And as I've seen from the hardware diagram, that you're using, let's say, 6 general purpose ARM processors. What is the special features of the SPRESENSE, let's say, compared to other popular devices like Raspberry Pi, where you could also do some, that from the hardware perspective, I have not seen, special hardware accelerators or GPUs that could speed up audio processing, something like this. So I would like to know what is kind of this key features that this PRESENSE hardware provide.
Okay, thank you. Yeah, one big difference, especially between the Raspberry Pi, is the much lower power, and so this device can work by with how to say the small battery. But usually the Raspberry Pi is, of course, Raspberry Pi is a much higher processing power. but need big battery or how to say power supply, AC supply or something. So that is a most different point. But there are 6 cores, and so if you can program the parallel things with using the 6 cores, then the performance is imaginary by 6. So higher processing performance, but lower power. That is a SPRESENSE the how to say the feature
Differentiation. Okay.
Yeah.
All right. Thanks. Yeah, makes sense.
Okay. Thank you very much. And let's move now to the third section of this embedded working group meeting, which is the panel discussion about providing a C++ API for micro-ROS. And I will let Jan lead this section. Please, Jan, you can start sharing or...
Yeah. So do you see my screen?
Yes, we can see your screen.
Okay. So basically, we have received a number of requests for C++ API for micro-ROS, and one reason why you can't use, and therefore I created this ticket here in ROS2 RCLC. So everyone who's interested can also look up the stuff what I'm presenting here. And the main reason why we went for a C API is that the default RCLC PP uses a lot of dynamic memory allocation, and in C++ there are lots of SDL containers, which is problematic in microcontrollers due to memory fragmentation and potentially having no control over how much memory is being allocated. Therefore, we went first of all for a C API where you have to define upfront how much memory you want to use. But now we have received a number of requests if we cannot provide a C++ API. And I made a first look in the structure or what kind of possibilities, what kind of options we have. And essentially, you could have a very thin layer on top of RCLC and just have a number of wrapper functions. Or you could also completely write a new RCLC PP layer where you only have static, where you don't have dynamic memory allocation, and would have to re-implement the entire, so to say, functionality of RCLC in the mainly. And here I made, let's say, a comparison of RCLCPP and what I would call micro-RCLCPP. So that's basically a thin layer on top of RCLC, and just technically thought about, okay, what needs to be done? I mean, how difficult it would be. And just because we are already running quite late in this meeting, I will just maybe go briefly over them. And I think so. The first thing is message type conversion. So in C++, you have typically a template argument providing the type of your subscription, and that needs to be translated to ROS EDL type support structure of RCL, and we could reuse this kind of conversion function in a similar way in let's say micro RCLCPP. The second thing is callback function pointers. So in C++, of course, you have no restrictions regarding function pointers. You can use member functions or lambda expressions, and in the callback itself, you have a message type as your argument, as a parameter for the message type. If you have a C library below, then you need to make and currently the executor is implemented in C. So the executor needs to call those functions, and therefore we need to have a translation between C++ function pointers and C standard function pointers, and that requires that you only have static member functions or capture-less lambda expressions. I mean, capture is basically a way to store a context or this pointer or something like this. I looked also in the internet. There's also an article about how to use real member functions as C functions, but that's kind of a template magic a little bit that basically translates this pointer into a function call having 2 parameters. Let me just go over briefly the other things, and that is message data types. So typically in C++, you can have static or dynamically allocated messages, for example, std string or SDL containers. Because you're working on a microcontroller, you want to avoid as much as possible dynamic memory allocation. So std string in C++ or SDL containers should not be used in that sense. I mean, the user can use it, but with the consequences of memory fragmentation. That's basically restriction or limitation on the user level. And the last thing, it's kind of more syntactic, is that in RCLC PP, you have a node where you add a subscription, publishers, timers, and so on. Whereas in RCLC, you don't have the concept of a node. There you directly add subscription, publishers, timers, and so on to the executor. But we could basically wrap the executor in a special structure for a node. That should be possible. So looking at these things, these are kind of features that need to be developed, but nothing is really blocking, right? I mean, we would have a thin layer of C++, where you have all the supports feature complete. However, with the restrictions that the callback function pointers can only be static member functions or capture-less lambda expressions, and you have not the type. You cannot write the type in the arguments of the callback function, and no dynamically allocated messages. So I would, just to wrap it up, so I wrote down here a couple of questions. We would like to know from you, for those people who are in the call here, maybe can share their requirements for a C++ API, and would these limitations and restrictions described above be tolerable for you? Would be okay. And then this can only be a community effort. So we at Bosch and Eprosima alone cannot do this development of C++ API. So it would be nice to know to what extent you could contribute in terms of, for example, code development, being a reviewer, or for testing. And also after this meeting, please feel free, just comment here on these questions. But I would like to open up the floor and maybe get some feedback from you regarding these questions, or just general comments as well. Or type in questions in the chat, whatever.
I would like to add, if you have ideas for more features, also those are welcome. So to understand what could be possible with a C++ API, what could be possible without requiring containers, and to understand, let's say, different levels, what could be designed and implemented, and then decide together what's the right level to really develop together.
Maybe directly do it for Sony. I mean, now you're probably implemented everything on C. So would C++ API be of benefit for you, or where would you see a benefit when micro-ROS would support a C++ API?
Is that a question for us?
Mm-hmm. I directly just want to ask you.
Yeah, actually, that's a good one. Yeah, we are. I don't know very much about application. I mean, like we are not a business unit, so. But most likely the application is constructed based on C++ for now. So as far as I see, if the library supports C++, they're going to be happy. Yeah, that's what I want to say. But we can do implementation with C if it's just like a trading off, right? So instead of it's C++ is useful for the implementation, but if we care about performance and etc., we do that with C. So, yeah, but we are happy to have that feature.
Mm-hmm. Well, also in terms of performance, there will be, I mean, will be comparable to RCLC because all the functions are in RCLC, and in the beginning you have to set up the objects. But once you call spin, all the functions actually in the executor remain in the C layer. So of course you will call the C++ function, but there is no, let's say, RCLCPP layer on top that has shared pointers and all that stuff. So performance-wise, exactly the same functions are called as you would have in the C application.
Yeah, exactly.
And kind of limitations that you can only have, let's say, static member functions. Is this a problem, or is this something that I mean, you have to look first for any comments on that?
Yeah, the static memory application sometimes required, but the product that we have is not exactly mission critical. I mean, like we most likely do like application for the entertainment, right? So. So, for example, the dog robot Aibo is not based on the C, but C++.
Okay.
Yeah, so we are not that mission critical application, but I mean, like it depends on the use cases, right? So maybe the car or some factory application that is the static memory application required. Yeah.
Mm-hmm.
Yeah.
And maybe just another comment. So the development of the C++ API on top of RCLC can also be used in ROS2. So of course it's designed for micro-ROS, but as it's based on RCL, you could have also, let's say, if you're talking about automotive or some other applications, if you just want to have a more static way for your application, this RCLCPP, this micro RCLCPP, can be just used on any ROS2 system. So
yeah, that sounds good. Yeah.
Okay, I think that this topic needs some more time, I believe, to get deep in discussion. So we will make a follow-up of this panel discussion in the next embedded working group meeting because it's relevant enough and it is worthy. Now we are running out of time. But before wrapping up, let me check if we have some topic in the miscellaneous section.
Yes, super quick. I have had a couple of community contributions that if you are interested in, you can check the links. But they are a couple of ROS discourse posts that I have seen. And I thought that they were interesting.
Okay, thank you, Pablo. And also, I have added a project, an R&D project called AquaSign from a company called Revetronic in Japan, and that uses micro-ROS and ROS2. And this project is about mobile platforms in the water with an actuator that is a laser. They use the topic twist, the command bell, and have a couple of booleans to activate and deactivate the laser. Well, all the information is in this link in this presentation. And also I have added a link of a short video from YouTube of a demonstration. The authors and all details are in the presentation link here. So we have reached the top of the hour. Before finishing this embedded working group, I want to thank everyone for attending, especially the speakers. Great contribution. I will be sharing the recording of this meeting shortly, and we wish you really good holidays, and we'll see you again back in September. Okay, so bye everyone.
Bye.
Bye. Thank you very much.
Thank you.
Thank you.